everybody, and welcome to our net zero building video on continuous improvement insulation strategies for net zero homes. We're going to be talking insulation and the things you need to think about, and the new approaches that are going to be coming at everybody, I think, as the building standards for energy efficiency keep tightening up. I'm very pleased today to be joined by a couple of really great experts on this topic. We've got Andy Cockburn. He is the Director of Education for NAIMA Canada. And we also have Gary Sharp, the Senior Technical Advisor for NAIMA Canada. I'm going to let these two gentlemen introduce themselves, and then I'm going to step out and let them get right into their presentation. So Andy and Gary, take it away.
Great. Thanks, Patrick. And so I'm Andy Cockburn. It's nice to be here and with my colleague Gary. And we're both working with NAIMA Canada. We're a nonprofit association representing mineral fiber insulation manufacturers in Canada and North America. Let me see if I can share my screen here with you. Oh, no, it doesn't seem like I can.
One moment here. Sorry, let me get the permissions on there.
Well, in the meantime,
sorry about that.
Myself. I'm Gary Sharp, and I'm the Senior Technical Advisor at NAIMA Canada. My background is I've been involved in the housing business for over 30 years now, and been involved in a lot of high-performance housing, right from R2000 through to net zero housing.
And with that, NAIMA Canada has been advocating for optimized insulation levels for 20 years. And I'm going to play off of Gary's experience here and ask him a bunch of questions. The story about building energy efficiency and how we make our buildings better has been around a lot longer than 20 years. So Gary, how did we get here? How did we get to net zero?
Well, Andy, it started back in the 1950s with a bunch of really smart researchers over at the National Research Council. And they started studying buildings and how to make buildings better. And they put together a series of building digests. These things ran for several years, and there's over 200 of them. But it really kicked into gear in the 1970s when we thought we were running out of oil around the world, and we wanted to make our buildings more energy efficient, to use less oil. And so R2000 and the super energy efficient home was started. The R2000 project, or R2000 program, really kicked it up a notch. And from there we went on to healthy housing and super E housing, advanced housing. Just a variety, including equilibrium. And right up until today, and net zero housing. So it's been a long time. We've been at this for 60 years or more.
And we're at the point now where we are seeing, even incorporating into new construction projects that are happening all across the country, where exterior insulation is incorporated. So what is it? What is continuous insulation? What does that mean?
Well, continuous insulation is essentially exterior, or could be interior insulation, but the insulation goes all around the entire building. So there's no spots that have no insulation. So the wall connects, the above grade wall connects to the foundation wall, which connects to the insulation under the foundation slab. The exterior wall insulation also connects to the ceiling insulation. And so the whole house is completely surrounded by insulation.
And you've got many layers in there that will contribute to that. And we'll get into that in a sec. But I want to know, continuous insulation, is it just new? Or can it be used on retrofits? Can it be used on both? Why or why not?
Sure. For new housing, of course, it's much easier to do continuous insulation because it goes in at the time that the building is being constructed. For retrofits, if you are doing a siding replacement, for example, then that's an ideal time to put some continuous insulation on your above grade walls, and add it there. If you've got a house that has brick or stone or some exterior cladding that you don't want to take apart or damage, then really the only option for you is to add the continuous insulation to the inside of the house. And that, of course, would reduce your floor area a bit. And a lot of people don't want to do that because floor area is, premium. So, but it is certainly possible to do it. A deep energy retrofit on an existing house would definitely have continuous insulation.
Okay, let's back up a bit here and talk about the conceptual piece. What
Sure.
is net zero? What does that mean? Who manages this thing? Like, who's looking after it?
Okay. So what net zero is the it is the ability of the house to produce as much energy over the course of a year as it consumes over that time period. So if you think about it, the way that the house is generating as electricity is from renewable sources. So let's imagine that that's photovoltaic panels mounted on the roof. So once you've got a plan for the house and you design, how big is the roof going to be, we can easily calculate how much energy falls on that roof and how efficient the solar panels are. That will tell you how much energy you're going to have available over the year to power your house. So the next step is to design the house so that it doesn't use more energy than that. And that means lots of insulation. It means better windows, better doors, all those kinds of things. So the net zero housing, the building code is looking at a tiered approach, or they are doing a tiered approach, where the top tier in the building code is actually net zero ready. So net zero ready means that the house meets all of the requirements for net zero, but has not yet had the renewable energy systems put in. And a few years ago, the Canadian Home Builders Association established a labeling program that they offer to their members, so their members can voluntarily build houses to this level of performance. And if they meet that requirement, then CHBA provides a label for them for either net zero or net zero ready.
Okay, and let's talk about those nuts and bolts again that you mentioned net zero. When you get to the point where you can figure out, okay, how much power do I need? What are we talking about layers? What are we talking about performance?
Sure. The results of the net zero program so far, there's been over 1,000 houses constructed. And if we say, well, what do they all have in common? Well, this is some of the things that they have in common. They are super insulated. So by that, I mean, R10 or more underneath the basement floor, R30 to 40 in the basement walls, R40 and up on the above grade house walls, and R60 or more in the attics. They have very strict air tightness, at least the R2000 level of air tightness, which is 1.5 air changes or better. But many of the builders are recognizing that making a tighter house allows you to save more energy. And so they're trying to get under 1, and in some cases, they're trying to get down to 0.5, and they're doing an amazing job at getting themselves there. The other thing would be high quality or high performance windows, so triple glazed, low E, argon fill, insulated spacers between the glazings, that type of thing, and high performance doors as well. And so, of course, whenever you build a house that's going to be tight, you're going to want to make sure that you've got mechanical ventilation in that house, and that you select the materials inside of the building envelope to be good in terms of indoor air quality. So no off-gassing, very low VOCs, but you manage that using the mechanical ventilation. And then because the net zero houses are producing energy as electricity, typically with photovoltaics, the mechanical systems are likely to be run with electricity. So we're seeing cold climate air source heat pumps installed. These things can go down to -30 or -35 C and still produce heat. And then we're seeing the backup for that being electric furnaces. And in addition, the water heating is quite often electric heat pumps now. So, and then of course the potential for renewable energy. So that the roof has been sized to accept a photovoltaic array that whenever the homeowner wants to put that up there, that at that point it would produce as much energy as the house is predicted to use over the year.
So envelope is important, and there's a couple of things you mentioned uh, about solar positioning and why we're putting on continuous insulation. But does it matter what the house looks like? What's the shape of the house? Does that really matter in the big scheme of things?
Sure. What we're going to see, I believe, is we're going to see houses that are more rectangular in shape. Because if you imagine that you have a corner or you have a bump out on a house, there's more framing that's involved in creating that bump out or creating that corner. What you're looking at here in the slide to on the picture on the right there is you're looking at a thermal camera shot of an exterior wall and window. Well, it's pretty clear there on the wall side is you can see the cold spots. You can see what the studs essentially, which go from the inside of the wall to the outside of the wall, and those become thermal bridges. So any place where we need more framing, like a corner, will become a thermal bridge, or a bump out would become a thermal bridge. And when we're working with the level of energy that we're trying to produce, the amount of energy that the house is going to use, we want to minimize the amount of energy that the house is going to use so we don't have to have extra roof area, or we're not creating energy that will be lost through this thermal bridging. So in part, the continuous insulation around the building is a response to thermal bridging and to stop or at least limit the amount of thermal bridging that's happening with the house. And from this picture, what I'd like to point out is the window. You can see around the edges of the window, especially at the bottom of the glass, it's looking very cold. So insulated spacers between the glazings will help to make that window warmer on the inside of the building. That will result in less condensation on the window, even in the wet rooms, like bathrooms and laundry rooms. And that's all of those things are going to help to reduce the amount of energy that the house needs in order to stay comfortable for the occupants.
Okay, I'm getting what you're saying. Now let's go from top down.
Sure.
What does that continuous insulation look like in the ideal situation? Because we're dealing with some historical kind of assemblies that make that challenging, right? Can you describe, like, if we go from the attic down, what are we looking at?
Okay, well, let's look at the picture on the left there first, in the lower left. That is a traditional roof that we built in the 1970s, 1980s, and prior to. So the ceiling joist sits on the wall, and then sitting next to the ceiling joist is the rafter, or this could be a truss, but the rafter is also sitting on the wall. So in order to get the insulation in the ceiling, it was cut typically at an angle and then slid in so that there was an airspace between the insulation and the roof deck. And that allowed for ventilation from the soffit on the outside of the house, that where the air would move up through there and out through vents in the roof. And that way we got our roofs ventilated. But the downside of that was that there was a reduced amount of insulation over the wall. And so that attic or ceiling to wall connection was always a cold spot. So if we look at the picture on the right there, the way that we've resolved that through, since R2000 and beyond, is that we now build or buy our trusses with high heels. So that's called a high heel roof truss. So if we look at this picture, you can see how the insulation is the same depth all the way across the whole ceiling, including over top of the exterior walls. So we haven't lost that amount of insulation. That exterior wall to ceiling connection is now a warm spot. We can also add the continuous insulation to the outside, which runs right up over that high heel roof truss and makes it continuous. That's part of the continuity of the insulation barrier around the building.
And you can do the same thing with cathedral ceilings, is that right?
Sure, you can. So in this case, showing a cathedral ceiling, you've insulated in the wall cavity. You're also going to insulate in the cavities of the cathedral ceiling, but around the outside of that, you can add your continuous insulation, and that will stop any thermal bridging all the way around the whole house. But this is actually pretty clear as to how the insulation connects and demonstrates that continuity. The ventilation that's required for that roof would still come from the soffits, but the air would move above the insulation, the rigid insulation or the exterior insulation there, between that insulation and the bottom of the roof deck. And that's how that roof would get ventilated.
So no big attic cavity to worry about there. You can just go right up over the top of the roof.
Correct.
Okay. Now, we kind of touched on exterior walls, but earlier we were talking about how R2000 and programs like Equilibrium set up the stage for not only insulation but other layers in there. What are we dealing with when we're dealing with insulating to the exterior? How does that work for siding or like for where the air barrier's got to go?
Sure. Well, the air barrier for a building, it doesn't matter where the air barrier is located in the wall system. It just matters that the air barrier exists and that the air barrier is continuous around the whole building. So the only barrier that you're worried about in terms of location would be the vapor barrier, and it needs to be on the warm side of the building envelope, or at least not more than 1/3 of the way into that insulated part. So if you could use a variety of different things. You can use an exterior air barrier. You could use an interior air barrier. Wood cladding on the outside, or not cladding, but wood sheathing on the exterior could be an air barrier with the joints taped. Rigid insulation can be an air barrier with the joints taped. There's just a variety of products that are available now to help builders to use an exterior air barrier.
Okay.
And if that exterior air barrier is insulating and you put on extra thickness, the only difference between the way you were doing it when it was thin and the way that you might be doing it now that it's thicker is the length of your screws.
Right.
So as long as you're still going to use the same approach, you're just going to use longer screws to do the job. You're still going to have the insulation layer there. You're going to put some strapping on the wall and fasten it to the studs on the inside, and then you're going to hang your cladding on the outside.
And Gary, I want you to explain this. This drawing is basically showing that we've got cavity insulation. We're going inside to outside, from the warm side to the cold side, and that one term right in the bottom right there, effective assembly. What is that? What does that mean when we're talking about the parts and pieces, like you're saying, all these barriers and exterior insulation? What does effective mean in this case?
Okay. So what effective means is if you look at just the wall part itself, so the studs and the insulation has a value, an R value, and let's say it's 22. Well, the structural components of the house typically have got an R value as well, but they are significantly less of an R value than the insulation material. So the structural components being concrete, wood, steel, those are all, they have relatively low R values. So in this wall, for example, that the studs that are there, they connect from the interior warm side to the exterior cold side. And because the R value is low, that's the route that any heat is going to take when it tries to get out of the building. So by putting an insulation layer over top of those studs, that provides a thermal break. Now, because the wall system has got studs in it and it has insulation in the cavities, the nominal value of the wall would be whatever the number is that's written on the insulation. So the nominal value of that wall is R22. So in order to find out the true insulation value of the wall, it's called the effective insulation, because the studs are all losing more heat than what the insulation part is. So there's a calculation that's done based on the number of studs in the wall to take into account what's the blended R value really of the heat loss through the studs and through the insulation. That becomes the effective insulation of the wall system. So let's say that's R18 for if you've got R22 bats and studs, and you do the calculation, you may come up with an effective R18 for the wall. Now, as soon as you start to put the exterior insulation in, because there is no thermal material or a thermal bridge going through that insulation, whatever the effective value of that or the nominal value of that insulation is, it's additive to the effective insulation of the wall. So let's say you've put R10 on, then your R18 wall becomes an R28 wall. And if you put another R10 on, it becomes an R38 wall. So every bit of the exterior insulation goes right to adding to the R value of the wall.
And you get the same kind of deal when you're dealing with something like cantilevered or projecting floors, where, like you said earlier, creating that thermal break all around.
Yes.
In this case, we're dealing with the bottom side of the floor joists that are hanging out in space there. Is that correct?
Sure. So imagine that, on your floor joist, if it's dimensioned lumber, it's a piece of 2x10, for example, sticking out of the building. That is going to allow for good transfer of heat from the inside of the building to the outside. And even if it's a wood eye, you've got a 2x piece at the top and a 2x piece at the bottom that are going to be, thermal bridges. So what you want to do is encase those in continuous insulation. And I think here it's pretty clear. You're going to fill the cavity of the floor joist, cavity between the floor joists that is outside of the wall. You're going to fill that completely. Then you're going to add some continuous insulation to the underside of the floor joist to prevent the thermal bridging. And you're going to connect that to the continuous insulation on the wall, so that it's all the whole building is surrounded by insulation.
And this segues nicely into what we would do on the next layer down, dealing with the foundation wall and connecting up to the floor system. How does that look?
Well, you can see here we have a slab insulation, continuous slab insulation underneath the entire basement floor. And then in this particular picture, we're showing exterior insulation on the concrete wall on the outside. Now you'll notice that at the bottom of the wall, the insulation on the outside goes to the bottom of the wall. The insulation on the inside is also connected to the wall. So that essentially in that lower level of the wall, that sandwiches the concrete between two pieces of insulation. So that prevents a thermal bridge at that location. And
Okay,
then
and
the
you've all
full height insulation, of course, protects the entire wall. There's the insulation should go full height of the wall,
and you could do this inside and outside.
inside and outside. Yeah, as long as the insulation is continuous and connects from one to another, like from one wall, the insulation on the foundation, for example, connects to the insulation that's in the rim joist, which connects to the insulation which is on the above grade walls, and that connects to the ceiling and insulation, and so it goes all the way around the whole house.
And you get that added bonus if you've got the continuity of insulation and air tightness all the way around, that you could also be mitigating radon. Is that correct? With that
Yes,
tightness?
yeah. Well, radon is a soil gas, and so if your house is depressurized, radon will leak in through cracks and holes in the lower level of your house, in your basement. And so if you have gone to, if you've paid more attention to detail and you have got a house which is tighter, there is less opportunity for radon to leak into that house because it has fewer holes. Now, if
Right.
all the holes are in the basement, of course, then radon has the potential to leak in. But radon is one of those things that you can't predict if your house will have radon. So you build as tight as you can, and then the occupants, who people that are going to move into that house, they should test their house at some point for radon and see if radon exists. And if it
Okay.
does, then it's a pretty straightforward process to mitigate radon.
Right. Speaking of basements and or no basements, uh, this funky thing where we're looking at a house that has a floating slab, it really has continuous insulation, doesn't it?
Sure. In this case, like so traditionally what we've done and today, we dig foundations and we put our houses so that the um, footings are down below the frost line, and typically the concrete floor in the basement is below the frost line. But we don't need to do that. We know how to build a slab on grade. So what you want to do is make sure that you've got a drainage layer underneath the foundation and around the foundation to keep any water out from under there. You want to insulate completely under the foundation and up the side of the slab, and then that connects to the insulation in the wall system. So again, it's continuous all the way around the house, and the drainage layer, of course, keeping water away from the house. You can see the drainage pipe in there as well. But the other feature that builders do here and our architects call for here is the skirting. So you can see the skirting, which is underneath the topsoil. It's on top of the drainage layer, and then the grass is there. So that skirting extends out about 4 feet or farther in some areas. And what that does is it prevents the frost from going down along the side of the house and getting in underneath the slab on grade. Of course, if as long as there's nothing in the slab on grade that you're worried about freezing, like water, then it doesn't really matter. But this is a bit of a belt and suspenders approach, in that you've got good drainage, get the water out from underneath the foundation, add that extra bit of insulation to make sure that it stays warm down there as well, and you've got a great foundation system with slab on grade.
Great. Lots to learn, lots to think about. We got a lot of challenges ahead, and we know that to get to where we need to be in terms of understanding net zero and understanding the stuff that Gary's talking about, it's going to take a lot of training, a lot of boning up on this material and finding out more about it. NAIMA Canada has created a whole bunch of free online training that deals with fundamental building science to train contractors, renovators, and even students in trades training in colleges and universities across Canada, and encouraging builders who are out there now, or even energy advisors and people that are in the industry, to get familiar with the stuff that Gary's talking about. It's not rocket science, it's building science, but it really does help to have that little extra boost for you. And this is why we created the training. And I wanted to get your thoughts, Gary, as well. There's there are new people that we need to get to know on our sites, and so the hierarchy of the construction project is going to change a little bit. Who else is going to be there?
Sure. Well, I mean, typically our builders have got their team, it's the foundation guys and the framers and the roofers and the electricians and plumbers and so on, ceramic installers. A couple of additions to the team. One of the first ones might be an energy advisor. And the energy advisor, what they do is they take the plans and they run a simulation through a computer program, and they can tell you how much energy that house is going to consume over the course of a year. So I think you'd start with how much energy can we collect on the roof? Then we'd run the simulation on the house and say, how much energy does the house need? If the house needs more energy than what's available on the roof, let's make the house more energy efficient. And then that'll get the energy down. And the ways that we're going to do that is by adding insulation, improving the windows, and making the house more airtight. Well, once we've done that, we want to make sure that we actually have gotten the house more airtight. The insulation's pretty straightforward. We can walk around and look at it while it's being installed, and you've got the right amount there. But the airtightness is a little bit different in that you can't see it until you test. And so then you do a test and make sure that the airtightness is one air change, for example, if that's what the design was, and not 5 air changes, because the house is going to be a lot harder to heat if the airtightness was not met according to the number that the designers were using. We're going to see photovoltaic installers, people that are installing the solar panels on the roof. That may be a new member of your team. And because we are trying to operate these houses as low, with as little energy as we can, it's going to be important that the mechanical systems that get installed are the right size and that they are commissioned so that we know that they're operating properly. And so you, as a builder, know that it's operating properly. So the days of doing the heat loss calculation for a house and then adding a safety factor of multiplying it by 1.5, for example, and putting in a furnace that is more than adequate for the house, I think those days are gone, and we're going to be sizing mechanical equipment to be much more in line with the needs of the house. And so once we do that, we're going to want to make sure that it's working properly. And so commissioning will be one of those things that you're going to opt for as we move forward.
To get to the point where we're at, where we can right size those systems, it sounds like we've got building envelope requirements that are going to happen
Sure.
in mandates. What does that look like across the country in terms of code?
Well, the Canadian government has said that we are going to reduce our greenhouse gas emissions. We're going to do that. In order to do that, what we need to do is to build our houses more efficiently and to upgrade our existing houses. So the building code is going to be used to make sure that all new houses built will be at least net zero ready. And so the National Model Code has a tiered system in there where tier number 5 is essentially net zero ready. Now, just if I can say a couple of words about that, is the National Model Code it's been done by the federal government to try and encourage the provinces and territories to harmonize with the national code. So the provinces and territories are responsible for housing regulation. And so the goal is that rather than all of the provinces and territories working on their own code and reinventing the wheel, each of them reinventing the wheel, back in the 1950s, the federal government, the National Research Council, started to produce a model national code with the intention that hopefully the provinces and territories would adopt that code, and we'd all be harmonized. So as in a few years ago, they put together what they called a reconciliation agreement that the provinces and territories signed. And what that agreement does is it ensures that the provinces and territories have said that they will adopt the national model code in a timely manner. And they have set up times by which that will happen. So as we move through this tiered system, the goal is that we will be at tier 5 or net zero ready sometime in the 2030 to 2032 time range. So 6 to 8 years, from now.
And remind us again, nuts and bolts. What does that look like for a net zero home for the construction person out there who's wondering what's that going to change? What materials? What are the systems going to be? What are the assemblies going to look like?
Well, likely one of the first things you're going to see is you're going to be finding yourself an energy advisor to help with that design. But overall, it's going to be something like R10 or better under the basement floor slab, R30 in above grade walls, or in basement walls, below grade walls, and R35 or above in above grade walls, and R60 or more in the ceilings. High performance windows and doors, and by that I mean it, triple glaze, low E, argon, insulated spacers, airtight windows and doors. We're going to see cold climate air source heat pumps. We're going to see heat pump water heaters being installed. We're going to be going for a much tighter house than what we're seeing right now. And as soon as we do that, we're going to want to put in an HRV or a heat recovery ventilator or an energy recovery ventilator in order to ensure that there is good indoor air quality in the house and that the air in the house is not stale or doesn't smell. So all of this to ensure that the occupant of the house is comfortable and healthy.
Lots to think about. Lots to think about. So thank you very much, Gary. And Gary Sharp is the one with a lovely mane of hair, and I'm Andy Cockburn. I'm the one without. Nice to have been talking to you today.
God, thanks, guys. That was a really great presentation. I feel like I could run out and build one of these things myself. But that's just how delusional I am. But that is that really was very well done. You nailed most of my questions. A couple of things that came to mind for me. Now I have heard, Gary, that you possibly can do some things with your wall thickness when you do continuous insulation. It's possible to use maybe a smaller stud space in there. Is that accurate? Have you heard anything like that, where you can get a little more room in your room by?
Yeah, I mean, if you've got the ability, for example, you could do say a 2x4 wall.
Mm-hmm.
2x4 walls were always used,
Yep.
in the early days, and there's no reason why we can't continue to use 2x4 wall. They will support a 2-story house without any trouble. That's allowed in the code.
Mm-hmm.
And then you could put all of the insulation exterior of that.
Right.
If let's say that you did a 2x4 wall, and then in order to make it structurally sound, you put 1/2-inch plywood on the outside as your sheathing, or 3/4-inch plywood on the outside. Yeah. And then outboard of that, you put all of your insulation. So you use a 12-inch screw, let's say, and you screw through your strapping and through the insulation and into the studs. And that's what is you're setting up to hold the insulation. And it's also going to hold the going to hold the siding that you're going to put on the house. So yeah, there's no reason why you can't do that. as long as you've thought about your insulation, that's one of the barriers, the thermal barrier. You've thought about how you're going to achieve your vapor barrier, okay? And the plywood could be the vapor barrier in that case.
Yep.
You've thought about how you're going to achieve your air barrier. So that could be the continuous insulation with the joints taped.
Mhm.
That would be one possibility. Or you could use a house wrap, or you could use a peel and stick membrane. Like there's all kinds of ways that you can achieve your air barrier. And then you're going to want to make sure that you also got a rain screen. So you've got your strapping, and then you've got a space before your cladding. And then whatever is the exterior there behind your strapping, whatever's on the insulation behind the strapping, that it's durable enough to be that rain screen as well.
Right, right. You mentioned rain screen, and it brings to mind window installation. What are the ramifications for putting your windows in when you do continuous insulation instead of the old style?
Well, you're with the extra insulation in there, you are going to have a thicker wall than what you've had before. So the option is put the window, on the inside, put the window in the middle, or put the window on the outside. It if you would have to put a plate there in order, like some kind of because you don't want to put your insulation directly on, or your window directly on the insulation, especially if it's a large window and heavy, without having something fastened to your sill plate that is going to support your window.
Right.
So that's going to control where your window is going to go. And with regard to adding extra insulation to your wall, if you've got a wall with a lot more insulation in it, you're going to want to make sure that the wall has the ability to dry in the event that it gets wet, but you're going to want to as well make sure that the wall doesn't get wet. So a good air barrier on the inside, or a good air barrier on the wall, is going to prevent the moisture that's in the air condensing in the wall. If it's leaking through, you're preventing that air from leaking through. So that's going to keep the moisture hopefully out of the wall. The other thing you're going to want to do is to put on better flashings, or do a better job with the flashings, so that we're not getting bulk water, rain and snow melt, getting in around the flashings and making the wall wet.
Yeah.
You can with regard to those plates Gary's talking about, if you think about Canada Wood Council put out a book a number of years ago, and I think CMHC had it in their library. It was the Canadian Guide to Wood Frame Housing. And one of the diagrams that they had in that book was showing Larson trusses, which are basically an outboard truss system that runs vertically that can hold insulation towards the outside. And we've seen this in some cases where in net zero passive house and those kind of things, they actually put I-joists on the outside of the building. The windows and doors themselves will get something akin to what they do in log building and timber framing that build out the opening, called a window buck. And basically all it is it's a meaty piece of plywood that's built in a box that fits into the rough opening. So you have to accommodate the rough opening a little bit to allow for that window buck. But that window buck then it fastens into the structure and extends out over that exterior insulation, so you still have structure there.
Oh yeah, that's a good solution. I think sometimes in Quebec I've seen where they just recess it back in, and the windows almost recessed back, but not everybody everywhere in the country likes that look. So we we have to account for regional differences, right? But yeah, that's that's a good one. Also, what about Gary, ramifications for getting in your the plumbing and the electrical? I mean, that's got to be a lot easier to do if you don't have all that batting in between the studs.
Oh, for sure. If you were using like a 2x4 stud, there's no you wouldn't have to put insulation in the cavities. You could run
Okay.
your wiring and your plumbing and everything right in those walls. And with the air barrier on the outside, you're not penetrating the air barrier unless you're putting in an exterior light or an exterior electrical box or a hose bib, for example, with the plumbing.
Right.
Now there will be a couple of holes from your HRV or your ERV where those ducts will have to go outside. So when you cut through the insulation, cut the size hole that you need for the duct and then foam those. Don't cut a 12 by 12 hole and put a 6-inch pipe in the middle of it, because that makes it really hard to seal.
It's so much easier though, Gary. Yeah, yeah, exactly. No, that's a good tip. Here's a question. Can you make a net zero house without this approach on the insulation? And what would that entail? How much harder would that be? How much more expensive would that be? Or is it just a question of approach? Who wants to tackle that one? I'll let Gary start, I guess.
Sure. Well, a tent would be a net zero house.
There you go.
But for people who actually want energy,
Yeah,
you could build the house. You could take any house right now,
mm-hmm.
and then you could put in enough renewable energy to provide the energy for the house. So that would make it a net zero house. Right. Now, we've had this concept for many years, and it hasn't been until more recently that the cost of the photovoltaics became acceptable to be able to do this approach. So where we could put more insulation in the house and get the energy load of the house down, that we could still afford to put some photovoltaics on the house to provide the energy that the house needs. So, I mean, typically what the people that are doing it right now are doing is they are collecting more energy in the summer than they're using in the summer, and they're putting that out onto the grid. So essentially using the grid like a big battery. And then in the wintertime, when they don't have quite as much solar energy available to them, they're pulling it off the grid and taking advantage of it. So they're pulling from the battery then, right? And so you could do it with batteries in your house, but typically it's being done using the grid because the grid's there.
Right.
So I think too. Sorry, Gary.
Yeah, you could do this. You could build a net zero house using conventional technologies, but you just have to add more solar panels would be the way to generate more energy.
The challenge too is, as Gary had alluded to during the presentation, that unless you've got a huge roof or you've got space in your yard or a large field where you can put an array, you really are pushing the building envelope to its maximum limits. How tight can you get it? How well insulated can you get it? And if you get it to the point where the building envelope and a tightness and its ability to keep the heat in or keep the cool in whatever time of year, if that is operating at its optimum, then that means that the systems that you need will be minimal. Mm-hmm. And it opens the door then for renewables, and it opens the door for feasibly running a lot of your appliances off of solar or geothermal or things like that. And historically, I know we've been doing this for thousands of years. I mean, they were doing it in ancient Greece, where they were facing buildings towards the sun, and they had a lot of brick and stone construction, and they would just warm up that mass with the sun. There's a story about an explorer by the name of Fridtjof Nansen, and he was around in the late 1800s, and he managed, while he was exploring the Arctic, he managed to turn his ship into pretty much a net zero passive house building by insulating the interior and sealing everything up with whatever he had on hand. And made a building that in his journals he wrote about and said, even the wood stove is too much for the inside of the ship because we've done such a good job of it. And so we've been thinking about this and doing this for a long time. If we can get builders to sort of treat it like a contest, who can get the best, tightest envelope that's the most thermally well performing, then we could have potentially net zero houses that hardly require anything to make them net zero in terms of systems?
I guess that's the question, because the term right now is net zero ready, right? Because they understand that not everybody is going to have the energy system on the house. They're not going to have the photovoltaics. They're not going to have a windmill, obviously. So there must be some standard to define what is net zero ready, because to Gary's point, anything could be, right? A tent could be net zero if it's not using any energy. So I guess that was my question: is does the insulate, like, is there some standard for the insulating value that has to be hit, and can you hit it to achieve net zero ready with a regular construction? Whoever wants to take that.
I'll take it. The requirement for net zero ready is that you have the space available to be able to install a solar array that will generate enough energy to meet the demands of the house.
Okay.
You finally get around to doing that. So okay. I guess the how much space do you have available on your roof? Because there's some excellent work that has been done to demonstrate that we don't have to have all of the solar collectors facing south at the perfect angle. Those will deliver the maximum amount of energy. But if we've got a lower slope roof, we could have collectors on the north side. They won't collect as much, but we know how much they will collect. We could put collectors on the wall on a south side. We could put collectors on the part of the roof that faces west or that faces east, and they will still collect some energy. So we've got, like, the people that have researched that have done a great job, and we know how much energy we can get from each direction, and it's not zero even if the panels are facing north. I mean, I don't know, you wouldn't want to put all your panels facing north, because you have to buy the panels, and I mean, if you're going to buy the panels and put them out, you want them to be performing to their maximum. But you have got other spaces available to you if you want. And there are companies out there that are working on solar siding, so you can put siding on the house and it has built-in solar collectors to it, right? So you can collect that energy as well.
You can also look, Patrick, to the amount of energy that net zero homes or net zero energy homes, they work around the idea that the amount of power that a net zero home should demand every year is 40 gigajoules. That's the ballpark you're working in. You're trying to get the envelope, you're trying to get the systems and everything that's inside the house that's working so that it has 40 gigajoules of demand every year. And then you apply renewables after that. In terms of the actual, like, how much attic insulation, how much wall insulation, and that kind of thing, the numbers that Gary mentioned earlier on, those are pretty much where you need to be. It will change by climate zone, obviously. Like, obviously in Nunavut, they're going to have different insulation requirements than in Windsor, but there are organizations now, I'm thinking of a couple in particular. There's Retrofit Canada out in Edmonton is doing work on releasing the details that they have on the retrofits they've done that get to net zero ready. So you can actually see, what did we do here and what are the parts and pieces? And at an official level, at a federal level, NRCan's LEAP program, the Local Energy Efficiency Partnerships, they have on their website now the LEAP Walls repository, which is basically they've taken 4 or 5 of the projects that they've helped to oversee across the country, and they've put very comprehensive information about what did we do in the attic, what did we do on the walls, systems, windows, the whole 9 yards. And you can actually see all the layers that are in those net zero homes. And so the difference between ready and net zero is basically, one is just the plug is there, and when you've got the money for the solar panels, go for it. And the other, you put the solar panels on and you're good to go.
Right.
But seeing examples of it, I think, is a really helpful thing for for people that are more inclined to go, oh, okay, that's how they did it.
Yeah, yeah, I should think so. And it's all trade-offs. I mean I've encountered this in the commercial side. I remember an architect was presenting and saying, the days of these long tall towers are going to be over because you don't have enough roof space for the photovoltaics, because you've got, the volume is all straight up and down. So who knows, maybe it's all back to bungalows, right? That could be the next thing. The last thing, guys. The uh, what is the uptake on doing continuous insulation across the country? Are there regional differences? How many builders are doing this versus still doing it the old way? I don't know who wants to do that one. Gary, go ahead.
Yeah, I don't have any statistics that I can just like off the top of my head, but I know from being out on construction sites and seeing it, we're seeing a lot of exterior insulation going in on with retrofits. Like, builders are installing exterior insulation when they're doing a reno, especially if the reno includes, siding replacement. I'm seeing more and more on new housing where they're using an exterior insulation that can double as an air barrier. So they're installing an exterior air barrier. And as you mentioned before, when you've got people that are drilling holes and, inside, the nice thing about an exterior air barrier is that you can walk around the outside of the building and look for holes. And if you see a hole, you've got a hole, fill it.
Yeah.
Like foam it up or do something with it. Whereas, with the interior air barrier, it's quite often difficult to find those holes.
Yeah.
Right. And the other thing is that, like with regard to, net zero and everything, we've been working on this like for 60 years with the National Research Council and Natural Resources Canada and CMHC and the Canadian Home Builders Association. And we've gotten the technology and the products, like new products that have come on. We've gotten to the stage where, we get to do this now. This is like what we've dreamed about, that we could build houses that are disconnected from the grid, essentially. And we can now do it. And we can, it's pretty exciting. It's like, we get to do this. We're not being forced to do it. We get to do it now. It's kind of
I
fun.
think an important thing too, Patrick, and I'm sure that Gary and I talk about this all the time because we're both building guys and we like to shoot the breeze, talk about shop stuff. Um, One of the things to impress upon any construction company, any retrofit company that's out there that's thinking, I wonder if this is something to get into. The great thing about this is we're not talking about something you haven't handled before. We're not talking about some weird assembly that is going to make you scratch your head for days on end. These are materials and methods that are pretty well understood, and most contractors have a great grasp of how do you install a piece of insulation, or how do you deal with a rigid fiber mat that's going to go on the exterior of a building. Oh yeah, okay, I need longer screws, and we're still going to do the strapping approach. Um, Anecdotally, there are pockets in Canada that are doing continuous insulation and have been for a while. And I know that there are some out there that are kind of going, "Wow, this is really new. I didn't think of doing this." But when you look at it, it makes sense. And most builders can easily wrap their heads around this. And it ends up being something that in the long run will make their clients more happy, the occupants are more comfortable, and in the grand scheme of things, we're using a lot less energy.
Yeah. Anecdotally, I would agree. I think it's something that most people who are looking at their designs are pretty much trying to go in that direction. Yeah, it's been uneven. It seems to be different areas are getting there, and hopefully with some videos like this, everybody might start thinking about it. I mean, it just seems to me to have a number of advantages over the traditional insulating approach. And you guys have no dog in the fight. You're the association for the insulation industry, and you like it too. So it seems like a good thing. Andy Cockburn, Gary Sharp, NAIMA Canada. What a great load of information. Thank you so much for joining us today on the Canadian Contractor Net Zero Building Show.
It's a pleasure, Patrick. Thank you.
Thank you.